Chapter 18. Rotational and Vibrational Transitions of Molecules. Section 18.1. Rotational Transition. The three-dimensional rotational energy of a two-body system is L times L plus 1 times h bar squared over 2I. L is the rotational quantum number. L can be 0, 1, 2, 3, 4, etc. I equals mu r squared. I is the moment of inertia. Mu is the reduced mass. The magnitude of the angular momentum of the 3D rotation is the square root of L times L plus 1 times h bar. The z component of the angular momentum is m sub L times h bar. M sub L is negative L plus 1, negative L plus 2, etc. all the way to L. Therefore, we have a degeneracy of 2L plus 1. The selection rule for the rotational transition is that L must change by 1 in a photon-induced rotational transition. So L can increase by 1 or decrease by 1. This is to ensure the conservation of the angular momentum, because a photon carries a spin angular momentum of h bar or negative h bar in the direction of the light path. As the molecule absorbs a photon, it inherits not only the energy of the photon, but also the angular momentum of the photon. There are two types of rotational transitions: rotational excitation, in which L increases by 1, and rotational de-excitation, in which L decreases by 1. In the rotational excitation, the energy change is positive. We can take the difference between the two energy levels from level L to level L plus 1. The difference is L plus 1 times h bar squared over I. In a rotational de-excitation, the energy decreases. Again, we can compare the difference between the two energy levels between L and L plus 1. The rotational energy change is negative L plus 1 times h bar squared over I. The angular momentum quantum number for molecules is denoted by J instead of L by convention. So when we are talking about the rotational energy of a molecule, a diatomic molecule, it's J times J plus 1 times h bar squared over 2I. J can be 0, 1, 2, 3, 4, etc. For convenience, we often define a rotational constant B in meter to the power of negative 1 or centimeter to the power of 1 this way. We define HCB equals h bar squared over 2I. So B can be expressed as h bar squared over 2HCI or h over 8 pi squared Ci. So B is also called in wave numbers. B is the wave numbers of the rotation. The three-dimensional rotational energy of a diatomic molecule can be expressed as J times J plus 1 times HCB. Again, B has a unit of wave numbers. The rotational constant B again is defined to be HCB equals h bar squared over 2I. Therefore, the three-dimensional rotational energy of a diatomic molecule is J times J plus 1 times HCB. When we are looking at a rotational excitation from J to J plus 1, the energy increases by this much, 2 times J plus 1 times HCB. In a rotational de-excitation from J plus 1 to J, the energy change is negative 2 times J plus 1 times HCB. The value of B can be calculated for a diatomic molecule given its bond distance and reduced mass. Taking hydrogen chloride as an example, the equilibrium bond distance is 1.275 angstroms, and we have the mass of a hydrogen atom and the mass of a chlorine atom. First, we can compute mu in terms of AMU. Mu is M1 times M2 over M1 plus M2, and we convert AMU to kilogram. 1.63 times 10 to the power negative 27 kilogram. Now we can compute the moment of inertia mu r squared. We plug in the value of mu and the bond distance. We get the moment of inertia for HCl 35, which is 2.644 times 10 to the power negative 47 kilogram meter squared. Now B is h bar squared over 2hci. This comes from the definition of the rotational constant B. B is defined this way: HCB is h bar squared over 2I, and therefore B is h bar squared over 2hci. We have the expression of B over here because h bar is h over 2 pi. We plug in all the values, we get the value of B, which is 1059 waves per meter. Sometimes we use centimeter to the power of 1 as the unit. Then B is 10.6 waves per centimeter. The physical meaning is this: within 1 centimeter we can fit in 10.6 such waves. Of course, within 1 meter we can fit in 1059 such waves. By convention, L is used as the rotational quantum number of electrons. J is used as the rotational quantum number of molecules. Molecules occupy various rotational energy levels at room temperature. The occupation number assumes the Boltzmann distribution. The occupation numbers are simply the number of molecules in various energy levels. So N sub j is proportional to 2j plus 1 times e to the power of rotational energy over kBt. Why 2j plus 1? That's just the degeneracy of the jth rotational energy level. Again, it's just because m sub j can be from negative j to j. M sub j can have 2j plus 1 different values. So with this taken into account, the number of molecules occupying the jth rotational energy level should be proportional to this degeneracy and also to e to the power of negative kinetic energy, in this case rotational energy over kBt. The rotational energy is J times J plus 1 times HCB. K sub B is the Boltzmann constant. K sub B is R over Avogadro constant. K sub B is 1.38 times 10 to the power of negative 23 joule per Kelvin. Taking HCl 35 as example, B is 1059 waves per meter. Now we compute HCB over kPt. Plugging on the numbers at room temperature, we get 0.051. And now N sub j is proportional to 2 times j plus 1 times e to the power of negative j times j plus 1 times HCB over kBt. When j is 0, 2j plus 1 is 1, and over here the rotational energy is 0, so this exponential function is 1. N sub 0 is proportional to 1. N sub 1 is proportional to 3 times e to the power of negative rotational energy over kBt. Here j equals 1, so on top we have 1 times 2 times HCB. and HCB over KBT is 0.051. So we can plug in that number here. We say n sub 1 is proportional to 2.7. What does that mean? That means n sub 1 over n sub 0 is equal to 2.7 over 1. Now let's look at n sub 2. The J value is 2, so the degeneracy is 5, multiplied by e to the power of negative rotational energy over KBT. The rotational energy is J times J plus 1 times HCB. So after we plug in all the numbers, we get 3.68. When J is 3, we get 3.79, and when J is 4, we get 3.24. So you can see from N0 all the way to N3, the occupation number keeps increasing. The relative occupation number goes up from 1 to 2.7, 3.7, 3.8, but then it drops to 3.2 when J equals 4. So if you look at HCl molecules at room temperature, I think more molecules occupy this third, this J equals 3 rotational energy level than any other rotational energy levels. Again, taking HCl 35 as example, B is 1059 waves per meter, or 10.59 per centimeter. So HCB over KBT equals 0.051 by numerical calculation. We can compute the relative occupation number, which is expressed as n sub j over n sub j equals 0. And this is equal to 2j plus 1 times e to the power of negative rotational energy over KBT. So we have this expression. Once we have this expression, it's very convenient to use Excel to use this equation and plug in the value of J from 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now we plot this n sub j over n sub 0, the relative occupation numbers from j equals 0 to j equals 1, j equals 2, j equals 3. You can see at first the relative occupation numbers increase as j increases, but after n equals 3, after j equals 3, well, it starts to decrease. The reason is because we have this exponential term here. When j is really large, this exponential function becomes really small. Given n sub j over n sub 0 equals 2j plus 1 times e to the power of negative rotational energy over kBt, we can maximize this function. To maximize or minimize a function, we simply take the first derivative of the function and set the first derivative 0. That's what I'm doing right here. I'm taking the first derivative of this function of the relative occupation number, and we get this derivative. This has to be 0, and therefore 2 has to be equal to 2j plus 1 squared times hb over kbt. And we set this to be 0 again. 2j plus 1 is the square root of 2 times kbt over hcb, and j is simply the square root of 2 kbt over hcb minus 1, and then divided by 2. Remember, we calculated hcb over kbt for HCl 35 at room temperature. The value is 0.051. So we plug in that value, we got this equation. We calculate the value of J sub max, which corresponds to the maximum occupation number. We found it to be 2.63. So if we're looking at a continuous function of this, well, the maximum is 2.63, so somewhere here. And no wonder we see this nj over n naught reaches the maximum at n equals 3 and it's close to the maximum when the value of j is 2. So this is our calculation. We got 2.63. So it's not surprising over here on this graph we achieve the maximum occupation number when j is 3. If you round up 2.63, it's 3.